everyone, and welcome to today's Open Teams community event. I'm Brian Skin, the community manager here at Open Teams, and I'll be your host for today. Open Teams is your one-stop shop for a range of services ensuring your success with open source, from commercial open source support to open source training, staffing, and recruiting services, and more. Visit openteams.com or reach out to us at connect@openteams.com for more information. As part of Open Teams' overall mission to sustain and support open source, we are sponsoring the Open Source Architect community with the goal of providing a dedicated space for experts to connect and collaborate over their favorite open source tech. To learn more or to apply for membership, visit openteams.com/OSA-community. We are also sponsoring the Engineering Manager community on LinkedIn, focused on fostering the career and personal development of engineering leaders. Visit openteams.com/EMC-LinkedIn to check that out. In today's event, I'll be talking to Jonas Mueller, co-founder and chief scientist at Cleanlab, a provider of data-centric AI software that automatically finds and fixes issues in datasets to increase the value of your existing data. He'll be taking us on a detailed tour of the Cleanlab open source project, which helps practitioners implement data-centric AI in their workflows. In this new AI age we find ourselves in, the importance and value of having high-quality data are both greater than ever, since AI and ML models can only be as good as the data they draw on. The concept of data-centric AI that's at the core of today's event is directly focused on this data-model relationship, and as we'll discuss, it seeks to give data curation refinement balanced attention with the model refinement that's the primary focus of conventional AI and ML. We are open to questions. Please send any you might have into the chat. We'll address as many as we can, either in the course of the event or at the end. We are recording the event today. That video will go up on our YouTube channel once we have it prepared. Subscribe there to be notified when it goes up, and I will drop a link to that in the chat. All right, with all that out of the way, let's get started. Jonas, welcome. Thanks for being here. Really appreciate it.
Thanks for having me, Brian. Super excited.
Looking forward to it. So before we get into the company and the project and the data-centric AI, tell us a bit about yourself. What's your background and how did you get into the field?
Sure. Yeah, I was always, as a child, pretty good at math and always wanted to do something that had pretty big impact. So I went to college, thinking like healthcare and biology are, really important to humanity and have, the potential for massive impact. Saw, the natural way to leverage math talents in those spaces was to do data-driven, projects like in bioinformatics and machine learning applied to these biological data sets. And over time, I just really saw, the generality of machine learning. I saw how techniques from computer vision, NLP, which had nothing to do with biology, were kind of changing, how state-of-the-art machine learning was being done in biology even. And just that the best techniques tended to be the ones that were really general. And so kind of just went all in on machine learning and more specifically like general machine learning principles that could be applied, across a variety of applications. And so after my PhD, I decided to go to Amazon Web Services and perhaps work on, the most general machine learning of all, which was building the AutoML services for Amazon Web Services, spanning computer vision, NLP, and structured tabular data sets. And as part of this AutoML work, our vision was to empower software engineers at any company to start, incorporating machine learning into their applications without being ML experts. And we saw that like on the coding side and modeling side, we were doing a pretty good job. So software engineers could take our AutoML tools and generate pretty good models for these tutorial data sets or benchmark data sets. But actually, when they tried to generate business impact in their company, they were still really struggling. And the reason just ended up being that the data sets they were using in their companies had all these kinds of issues in them, and really just saw time and time again that these folks that were not, formally trained in data analysis and how to clean up the data set were just unable, even though they had the modeling technology provided to them, they were not able to actually deploy good machine learning in their companies. And so really thought the next evolution of AutoML needs to be something that tells you, what's wrong with your data set before you should even get into, all the modeling side of things.
Yeah, I mean, that's what they say. Like in data science is what, data cleanup is like 80 to 85% of the work or something like that.
Yeah.
Only stands to reason it would hold true for AI/ML as well, right?
Yeah, and especially for newcomers to the field, they're sort of looking at, the literature in the field, and it's all this intimidating math about models and things like that. and they think, that's where they should be concentrating their effort on. But actually, yeah, there's, any seasoned data scientist will tell you they spend all this time just cleaning up the data, and a lot of it is just based on their experience and intuition, sort of this dark magic, much like, deep learning was once upon a time. And really,
Yeah.
we are trying to now automate that process to make it more systematic and less, just based on pure intuition alone.
Hmm. So then you made that move into they need, the non-expert practitioners need help with their data prep as well, and started chasing that. Yeah.
Yeah, and so going back to my story, back in grad school, I met two of my friends, Anish and Curtis, and so we were all grad students together. And Curtis was doing some research on trying to find cheaters in online education courses, and he realized the labels of like who's a cheater or not is super noisy, right? Because you never know for sure if somebody cheated or not in an online education course. And so we ended up publishing some research on algorithms to find mislabeled data automatically in a machine learning data set. And we, open sourced the code for that as part of the research. And that code ended up being used by all these companies like
Mhm.
Google and Wells Fargo and many others. And they were asking us for, enterprise support. And so over many years since I had graduated grad school, that library, which was called Cleanlab because it cleaned your data set labels, just kept being used by more and more companies. And working at AWS, I kept seeing, over and over that people are struggling with these data problems in machine learning projects. And so we really just came back together as a group and decided to create the company around Cleanlab, around this open source library. And since then, expand our mission beyond, just finding label errors or just, finding one kind of problem in data to being the best provider of AI techniques that just automatically help you improve data, whatever that may mean going forward in the future. AI is always changing, and we think there will be a lot of different AI techniques that emerge that are able to improve data in tremendous ways.
Hmm. And so we've kind of been talking adjacent to it, I think. So the term data-centric AI is kind of at the core here. Go ahead and, if you would, put a definition to that, and then I mean, I think you've described your efforts along the direction of data-centric AI, but then maybe, what is, maybe frame Cleanlab's mission in it from the perspective of data-centric AI, something like that.
Yeah, so a lot of people, have this confusion about data-centric AI. Like, what's new here? Isn't that literally just machine learning? Because old-fashioned AI was symbolic systems, and machine learning is saying, hey, we should use data. But really, the idea in data-centric AI is to really focus heavily on the data over the models, whereas in machine learning, the culture is still very model focused. So if you think about almost all your coursework in machine learning, right, it is teaching you the math behind different kinds of models, gradient descent, all of these different training techniques and different architectures, ensembles, gradient boosting, all that. And really, you're almost never taught too much about the data set. The data set is just kind of given to you throughout your years of
Mm-hmm.
education as
Mm-hmm.
this object, and it's your job to get the best performance on this data set. No questions about, why that's the worthwhile goal. Maybe I could change the data set. In the real world, if you're working at a company or an organization, they don't really care what you do to get, good performance in machine learning that actually improves the lives of your customers or users. Um, Really, anything you can do, including modifying the data, is totally fair game. And people know this. It's not like, this is a new realization. It's just the way people have been modifying data the past, 50 years has been totally manual. So like a data scientist will just dive into the data with exploratory data analysis,
Mm-hmm.
poke around Jupyter Notebook, think of random ideas on the spot, just based on their years of intuition, and just try them out, see what happens, and kind of iterate on this process. And there's a lot of problems with that. Like, it's just totally not systematic. You're missing a really large amount of recall because maybe you're checking the data for certain kinds of problems that you happen to think of in the moment, but you're not, running this huge suite like we would for software, right? We would have unit tests and we would run a huge suite of checks on all our software because we know in the moment there's no way you can remember all the checks to run.
Mm-hmm.
Um, and so really the idea of data-centric AI, as it's been commonly now adopted, as pioneered by Andrew Ng, is given a fixed machine learning model, we're going to actually switch to altering the data set itself and trying to see how can we change the data set to boost the performance of that machine learning model as much as possible. And so that's kind of the other extreme, right? Of having the data set be totally immutable and just only iterating on the machine learning model like you would have in your classes. And in practice, of course, you need both. But the idea that Andrew Ng was really calling for when he pioneered this term was that people are just not paying enough attention to that second way of working with
Mm-hmm.
machine learning model fixed and using the iterating on the data set to get better performance. And so that I would say today is the mainstream definition of data-centric AI. And at Cleanlab, we actually adopt a third definition, which is maybe a little unique to our company, but really the idea is that once you've trained any sort of machine learning model on a data set, it has captured a lot of information about your data. It's really understanding a lot, as these models get more and more powerful. And you should actually be using that model itself to help you find problems in the data systematically and algorithmically. And so we consider data-centric AI as well as AI that's specifically designed or used to find issues in the data so that, the AI itself is being turned on the data.
Sure, makes sense. No, the analogy, the loose analogy that comes to mind is if you have a complex, just even a non-AI, non-linear system that you're trying to optimize. Sometimes you have to decouple it and have one piece. You hold one piece constant and then optimize the other, then hold the second piece constant and optimize the first. But in order to do that consistently, systematically, and quickly, you have to have systematic tools, approaches for both of those. When you do that iteration on that half of the question, it just runs. You don't have to, to some degree, you don't have to have human oversight over every step of the process.
Exactly. And with, modifying the data, we do think there will always be some degree of human oversight because often, in the data set itself, the information of where the data came from and what you're going to use it for is not directly contained in the data values, but we want it to be as automated as possible and as systematic and reproducible as possible.
Yeah, yeah. When you were talking about talking through it as well, I was thinking of Kaggle. Like you're saying, you're often handed a data set and then, all right, optimize the model. Kaggle is, at least as I understand it, to have been kind of very much focused on the modeling side. Are there any similar organizations, competitions, or are there things starting to develop where there's data-centric AI sorts of competitions like that, where you have to both improve the data set and refine the model on it?
Yeah, there's been a few efforts in this vein over the last 2 years, I would say. Andrew Ng had one. You can search data-centric AI competition on, I think, his website, deeplearning.ai. We at Cleanlab actually hosted one in collaboration with this Kaggle-like platform called Machine Hack, and that was called the Data-Centric AI competition in 2023. And then more recently, I've been part of this group called DataPerf. So some of you might be familiar with this organization, ML Commons, that organizes MLPerf, which is essentially a competition on how to train ML models the fastest. And it's become like an industry standard benchmark. So this is a really big organization led by Peter Madsen that's hosting these competitions, and they're a really big deal in industry. And Peter's also, jumped aboard the data-centric AI train over the last
Mm-hmm.
years and started this new group called DataPerf, where the idea is to come up with new techniques that can algorithmically improve data sets. And the DataPerf organization has been hosting a few such data-centric AI competitions recently at most of the major machine learning conferences, especially.
Excellent. So definitely some broad traction for the idea and its importance. Excellent. Cool. Um, if that if you feel that covers yourself and data-centric AI and Cleanlab the company, any more details there if you want, or we can jump into Cleanlab the project, your choice.
Yeah, I guess so I'll just give a brief overview of our company, and like our mission, as I mentioned, was to use AI to try and help you automatically find and fix issues in data sets. And it's really a broad mission that we operate across all types of data sets, ranging from image data, text data, so unstructured data sets, to structured tabular data sets. And really, we try and develop techniques that are data modality agnostic and as general as possible. And we find often these simpler techniques, especially when it comes to data improvement, it's so easy to come up with techniques that are super specific to this one data set and this one maybe not even data domain, but just literally this one data set. And we
Mm,
try to avoid that in our software solutions. And so that's kind of the theme of what I'm going to present today with our open source library too, is exactly these really generic techniques that tend to work and help you across all kinds of data sets. And that really makes them powerful, I think. But of course, you can also do a lot better for any specific data set by using your domain knowledge. I want to just emphasize, this is not the end all be all. It's supposed to be a starting point to help you start systematically improving your data using algorithms to supplement, your human ingenuity and your creative ideas for how to improve data and catch issues.
sure. Kind of balancing the same. Oh, there's an analogous to the overtraining problem. You have an over data over data cleanup, custom tailoring sort of problem. You have to
Right,
watch out for.
right.
Yeah. Cool.
And yeah,
Yes.
over time, we do hope, as AI gets powerful, more and more powerful, it will be able to get more and more specific into, different domains like accounting. You can
Mm,
imagine an accounting data set has so many problems that are so specific to accounting, but we are seeing, with increases in foundation model capabilities that we are able to start doing more and more domain specific data cleanup as well.
nice. Cool.
Cool.
So
So yeah, I'll jump into a presentation here.
go for it.
Hopefully you can see my screen.
It's coming. Looks like it's coming through well. Yep.
Perfect. And so I'm going to talk now about our open source library, given this is the Open Teams group. And so the idea of our open source library is to be a standard framework for data-centric AI that you can apply to all kinds of data sets where you have a machine learning model. So I'll probably skip through some slides quickly, but yeah, going back here, we're seeing, 80% is roughly a figure that's tossed around a lot of time that tends to be spent on data preparation work and data cleaning work. And, top groups like OpenAI, Google, Tesla, many of these other top groups in machine learning that have developed some of the most beloved machine learning models, they are spending like a huge amount of human labor and money to curate these data sets to ridiculously high degrees that a lot of other people don't realize. And so, like this is the blog post from DALL-E 2. I guess it should be now updated to DALL-E 3, but the techniques are going to be the same. And they are just, making sure that the data in these that's used to train these models are as high quality as possible, because obviously, like if some of the data happens to have objects that are incorrectly labeled, like a plane labeled a car, then, models like DALL-E could be confused and create the wrong kind of object when a user requests it. Kind of an obvious idea. And same at Tesla and many others. And so our journey, as I mentioned, we had discovered using a very early prototype of the Cleanlab library that I'm going to present. This is an algorithm called confident learning that was essentially just originally a research paper on a way to find mislabeled data in a classification data set. So one kind of data problem, in one kind of machine learning data set. And we ran this on some of the most famous data sets in the machine learning space. So these are data sets that, hundreds of thousands of people have run benchmarks on. Getting any kind of performance improvement on these data sets is a really big deal. But we discovered using our algorithms that they're just full of label errors. And this had not been known before, which was very surprising to us. And yeah, so we ran it, on all these very famous machine learning data sets and reported, the different percentages of errors we detected. And this became featured, in many news articles and media. And that really led to the inception of our company. This was the early inception that led to our open source library, becoming popular and people starting to recognize this need for machine learning automated systems that can help you find problems in your data. And so again, just to reiterate, the view on data-centric AI, the traditional way of working would be the data scientist kind of is given the data, they improve the data manually, and then they switch over from data prep mode into modeling mode, and they spend, the rest of their time trying to go from some initial baseline machine learning model that they had first trained to like a better machine learning model by changing the loss functions, regularizers, hyperparameters, all that stuff. And in data-centric AI, the idea as we see it, and as we're going to present it in this talk, is that your initial machine learning model that you originally trained once you got your data properly formatted already knows a ton about the data, and you can use it with the proper algorithms to actually get a much better version of your data set. And then you can just retrain that same initial machine learning model on the better data, and it should already be better. And so that's like a totally orthogonal, way to get machine learning benefits. But of course, you can also, after you've done that process, go back to all your improved modeling techniques and just keep refining that model to get an even better machine learning model. There's no reason, modeling improvements and data improvements tend to be very orthogonal to each other, especially with the really flexible, huge neural network models people use today that are kind of just like data sponges and really absorb like all kinds of patterns in most data sets. And so our Cleanlab package that I'm going to present today can be found on GitHub and is open source and a Python library. And it's really one of the most popular libraries out there for data-centric AI, used by like all kinds of data scientists in all kinds of industries. And it works really across all data modalities as long as you're able to train a machine learning model for your data. So the ingredients for this library will be your data set and a machine learning model, and then the library will tell you a bunch of kinds of problems in your data. And the basic, minimal code snippet will look something like this, where you have your data set, maybe you have some labeled data, so you specify the label. And then we're going to provide some information from our trained machine learning model. In this case, say embeddings of the data. So these are the machine learning model's representations of the data, how it views the data, as well as predicted class probabilities for each data point. So this is how, it classifies the data and its confidence levels in its classifications. And with those two ingredients, we just say, find issues in this data set, and we'll get back a report that summarizes all kinds of issues automatically detected. And these issues can really span all kinds of different kinds of problems. So going back to this, mislabeled data is sort of the thing we're most famous for, automatically detecting, which data points are mislabeled, but we can also detect, which data points are anomalies or outliers that are semantically very different than the rest of the data. And these often may indicate problems with your data sources, like some unexpected data source may be getting into your data set. We can detect, nearly duplicated data, which are semantically very similar. And, if you're unaware of these being in your data set, you can often have modeling or analytics that tends to emphasize certain subpopulations in your data more than others, even though you didn't, intend that to be the case. If you're, unaware that there's heavy duplication going on, as well as other types of problems like non-independent data. Maybe you have examples that are actually highly statistically dependent or interacting with each other, and you didn't realize that. We can also detect more data type specific issues as well. So going to image data now, I want to emphasize that all these issues here, while they're shown for image data, the same concepts can be applied to text data, structured tabular data, really any kind of data. Whereas these issues here are going to start to be more, specific to image data. So, like detecting low quality of images of various types and other kinds of problems like strange aspect ratios. And as I mentioned, all of this can be applied to text data as well, where, in say customer service data set, we might have miscategorized customer service requests that are mislabeled, and other requests that may be ambiguous, and a bunch of other kinds of issues as well. And really the philosophy when designing the Cleanlab library that we take to heart, and I've, really tripled down on over, 10 plus years of machine learning research, is that simple methods are the way to go almost always. And so if we look at, a field with a really rich history, say outlier detection. So this is a research field, right, that has thousands and thousands of research papers published in it. And what you find is there's like two kinds of ideas. There's kinds of ideas that are really simple but they're very compatible with all kinds of models. So one example of such an idea is for detecting outliers, we can just get embeddings of all of the data from a model, so the representations of the data, and simply measure, the distance to the k nearest neighbors of a data point, and take the average distance as, an outlier score for that data point, and a measure of, how atypical it is. And that technique, can now be combined with an arbitrary machine learning model that can be used to produce representations or embeddings of the data. In contrast, you could also have really sophisticated outlier detection techniques, based on complicated probabilistic models and, statistical generative models that are designed for specific data types, or really they don't take in any machine learning model whatsoever. And maybe at one point in time, when such a method was published, it happened to be the best method available at that time. But what you see is that the more simple methods that are compatible with any machine learning model, machine learning models are just constantly improving and improving relentlessly. And so, 5 years later, now suddenly this really simple technique can be paired, with the latest and greatest machine learning models available today. And we find time and time again that, years later, that tends to be much, much better than whatever was the state of the art originally at the time the more complicated methods were published. And so our emphasis throughout this library is almost always to try and keep the methods as simple as possible, but crucially compatible with any machine learning model. So that keeps it really general
Yes.
and forward compatible.
One question coming in from the audience.
Mhm.
They note that since Cleanlab, the data-centric AI approach and Cleanlab's approach, you're using the production model, so to speak, the output from an early version of that to do your data evaluation. Since you're introducing that into that loop, and correct me if I'm summarizing the question wrong, questioner. If there's are there ways in which that production model that you're starting to use to get that initial set of output to run into the data-centric AI work, if there are flaws in the machine learning model, does that mean that you could have problems, that the errors, false positives and false negatives in the data cleaning, iterations, if there's some key flaw in the model itself?
100%. So yeah, this is the data-centric AI loop of model improvement based on fixing the data, and then data improvement based on your current machine learning model. It is a virtuous feedback cycle. Each iteration of that loop really depends on you doing something beneficial on the model improvement side or on the data improvement side. And so when the model is really poor on the outset, all of the techniques that I'm talking about will be less useful. Like, they are tied to how good your machine learning model is. There's no, free lunch that you can have a completely horrible machine learning model and then magically it's able to, these algorithms will help you find, great issues in your data. But on the flip side, as your machine learning models get better and better, even just with time, machine learning technology is always improving. All of the data improvement techniques improve along with it. So that's sort of both a benefit and a negative in terms of being tied to the machine learning model. And then if we're now talking about, precision and recall, say, of detecting different kinds of problems, 100% the precision recall or performance more generally of detecting problems in the data and fixing them will be tied to the weaknesses of the machine learning model. And it's important to consider whether you are introducing certain kinds of biases in your data if you're changing it too much. And that's why we generally recommend against fully automated data edits. Like, we always recommend there's a human in the loop when it comes time to actually edit the data set. And we are mostly using the machine learning plus the data-centric AI algorithms here to come up with detections of problems and suggestions maybe of how to fix them. But we recommend, like, the person who knows why the data were collected and where they're coming from actually carries out those data set edits.
Suggestions, not prescriptions. Yeah, that makes sense.
Exactly.
Yeah, great. Thank you.
Yep, awesome. And yeah, so like, yeah, keep that in mind. The performance of that initial model will really matter. And just like, with everything machine learning related, we're not expecting the initial machine learning model to be perfect. Certainly not. That's like what a lot of our work goes into in designing these algorithms and why it's challenging, right? Like, if the machine learning model were perfect, for example, to detect mislabeled data, it would be trivial. We would just always take the machine learning model's prediction as, what should be the right label and totally ignore the data and just rewrite all the labels in the data with the machine learning model labels and say, call it a day. But yeah, unfortunately, the real world is not so simple, and we have to account for the fact that the machine learning model is totally imperfect. And then finally, it's important to also just keep in mind what's the baseline we're comparing to. The baseline we're comparing to is just a human, doing this stuff manually, right? So a human doing it manually is also going to have tons of biases when they're coming up on the spot with intuitive fixes for the data set, they're going to miss, tons of issues themselves, right? And so using the machine learning model to help with that process, we see that just as a strict benefit, really. Like, for sure there is, it's not a complete perfect solution when the machine learning model is imperfect, but it's much better than just you doing everything manually yourself.
Indeed.
And so, yeah, going back to that point about, detecting mislabeled data, that's this field of research we developed called confident learning. And we published a lot of papers about this research, so you can go check those out. And I'm not going to get too into the details here, unfortunately, given the time constraints. But yeah, I recommend we have blogs and papers about it. And really the key idea here, like this, that was a perfectly timed question actually, is that, we can't just blindly trust the machine learning model trained on finite data, and it may be an imperfect model, to tell us, when the data is mislabeled just based purely on its predictions. So the first thing, obviously, we want to do is consider the machine learning model's confidence, right, in its prediction. So we consider the predicted class probabilities rather than just the predictions. And more importantly, we have to decide, when should we trust the model over the data itself, right? Like if we're saying this data point is mislabeled, we are essentially considering trusting the model over the data. And that means we have to understand the types of shortcomings in this machine learning model that it makes overall. So essentially the core idea of the algorithm is to figure out what kind of shortcomings does the machine learning model tend to have overall the data set. You can think of this like a global calibration measure for those of you who are familiar with like probabilistic calibration. And understand maybe like this model really, say you have like a dog cat classifier, and this model just hates predicting dogs for whatever reason, bad at predicting dogs. Like we should take that into account. Like if the model says an image is mislabeled as not being the dog class when the given label is dog, we should be suspicious of that, because we know this model tends to really not predict dogs properly, right? So that's the core idea of confident learning. And, the actual implementation requires a lot of math, and it's related to ideas of probabilistic calibration. But the core idea is figuring out those global shortcomings of the model, accounting for the model's confidence in its predictions, and basically then saying, okay, if the model is making a very confident prediction that's different than the given label, and we know for this kind of data, the model tends to not have shortcomings, it tends to be good at making predictions like this, that's when we're going to say, okay, probably this data point is mislabeled and is worth a second look. And just to show you, even if we're just talking about a simple classification data set and we're talking about just detecting mislabeled data, there's a lot of complexity that can come up in real world data sets. Here, these are, the cleanest of the clean famous machine learning benchmark data sets. And in real industry data sets, you just see much nastier instances of all these kinds of problems. But, we have different kinds of label errors, like non-agreement, where different annotators might, given the same example, actually disagree, what's the correct label, because it's hard to determine based on the information. And so that's something that our algorithms can help you detect. These are hard examples or ambiguous ones. Also, you may have forgotten to include like a other class that we see this all the time, where you should have, included the option to say none of the above to your machine learning model, but you didn't frame your problem in that way, and therefore you end up having tons of mislabeled data. Also, many machine learning problems are framed as, say, multi-class classification, where each data point has to belong to one and only one category, but actually they should have been framed as like image tagging problems or multi-label classification problems, where each example can actually belong to multiple categories because they're not actually disjoint necessarily. And finally, we just have, straight up errors that were probably made just due to human annotated error. And, there actually does seem to be a much better label in the data set. And I want to emphasize that these confident learning algorithms and our Cleanlab library can detect all these sorts of problems in a data set. And just to give you some basic benchmark numbers, one way to benchmark this stuff, of course, is you can introduce, label errors into a data set. And here we try and do this as realistically as possible, not, just randomly perturbing the labels, but doing it in a way that imitates human annotator error, the types of errors human annotators would tend to make. And the key takeaway from this slide is that there's two kinds of approaches in the machine learning research literature for dealing with such noisily labeled data. One is this data-centric approach where you're going to modify the data, and that includes, confident learning methods and a few other methods that like data augmentation strategies that change the data itself. And then there's actually model-centric methods that have specifically been designed for a specific machine learning model to alter, say, the loss function to pay less attention to stuff that seems mislabeled, or to add a regularization or something like that. And these are, deeply embedded in the model training process and are trying to encourage the model to be able to be more robust to mislabeled data, whereas the data-centric methods are just looking at the data set, identifying what seems mislabeled or modifying the data set in some way, and then retraining the model with no change in the model training procedure at all. And we just find that, these techniques are just much more performant than the model-centric techniques, which tend to be very brittle. They tend to only work for a specific type of architecture. So, 5 years from now, when there's new kinds of machine learning models that are trained in totally different ways, these techniques may no longer be applicable at all. And to give a concrete walkthrough of an example of how we could start using our open source library for a specific problem, let's consider a simple text classification problem where we want to classify how polite is some text in some online project collaboration software. So these are people's comments in some online project collaboration software where people are giving each other feedback on different kinds of projects. And we want to classify the feedback as neutral, impolite, or polite. And you can read the rest of the details in this article we published. And so we can just run our library on this data set and detect different kinds of issues in the data, such as mislabeled data, such as this one, that has been labeled impolite in the data set, but doesn't really seem impolite at all. And so the way we're going to do this is the ML model that we are going to use with Cleanlab. Remember, our open source library is always run together with a machine learning model. In this case, would be a fine-tuned OpenAI model. And here I'm starting to emphasize, the generality of the library. You can use it with any machine learning models. So why not just use all of the machine learning models that at this time OpenAI offered a fine-tuning API for? And so in black, what we are showing is what happens if I just fine-tune, say, the DaVinci LLM just on the original data, and then I measure its accuracy on a test data split. And importantly, the test data we made sure are well labeled, because we actually had multiple annotators inspect each test data point to ensure that they're well labeled so that these numbers are trustworthy. And so in black, yeah, we're showing, just fine-tuning the model on the original data set, measuring its test accuracy on the well-labeled test set, and what do we get? In orange, what we are showing is, okay, let's now take that original model, let's use it with our Cleanlab open source library, detect which data points seem to be mislabeled, just delete all the data that is algorithmically detected to be mislabeled by this confident learning algorithm, just all at once. So this is no human in the loop at all, basically, just totally automated, delete all the data that detected to be bad, and then refine tune this model once again on just the remaining data, and then measure its test accuracy still on that same test data set, so it's directly comparable. And we see you start to get performance improvement. And over here in these right two bars, or these right two subplots, it's the exact same process, just with a different OpenAI based model being fine-tuned. And then even better is, okay, we've detected, what data seems to be mislabeled. Let's actually go through that mislabeled data, or that data detected to be mislabeled, and manually review it and try and fix it up. And by doing that process, here's where you start to see the value of, having a human in the loop and actually, correcting data with your additional knowledge through that process, and then refine tuning the machine learning model on the resulting data set and measuring its accuracy. We see like even greater performance gains. And we want to emphasize, even though that process does involve some manual work, it is not like nearly as onerous as it would be just going through this original data set. Right here in the blue charts, we are only going through the subset of data that was algorithmically detected as being worthy of our time. And this is a tiny fraction of the original data set. We can apply the exact same approach for a tabular data set. In this case, now training, popular model for tabular data would be XGBoost or other gradient boosted tree models. And again, it's the same exact process. We can just use our XGBoost model with Cleanlab to detect the mislabeled data. In this case, the data is about student grades, where there's data entry errors on the students' final grades. And retrain that model after algorithmically just removing the auto-detected bad data, or we can manually review, that auto-detected bad subset of the data and fix it and get even better performance. And really just trying to emphasize that in this manual fixing process, a core aspect of what you might need is like a nice user interface, right, that allows you to quickly fix, a large scale data set all at, allowing a single data scientist to quickly fix the data. And for that, that's something our company provides beyond our open source library. Is we provide, as part of our software as a service solution, which we call Cleanlab Studio, we provide really nice user interfaces that are intended to help you efficiently fix up your data as quickly as possible. All of these ideas extend, beyond text classification to all sorts of machine learning tasks. I'm not going to have time to, go into every single kind of machine learning task, but things like RLHF, really the emphasis here is just to show that anywhere there is human in the loop, human supervision coming in with data, humans always tend to make errors. And the Cleanlab library used in combination with a machine learning model can help you automatically detect these errors. In this case, like in RLHF, the human supervision would be choosing, which of two LLM completions is the better one. And humans doing this task tend to accidentally often just choose the wrong completion. In this case, it's very clear that this is the better completion of the request. But for some reason in Anthropic's data set, this was annotated as being the better of the two. And the Cleanlab open source library used with a machine learning model can help you detect these kinds of problems. It can also help you better evaluate your machine learning models because, of course, when you're evaluating your machine learning models, you're also still critically dependent on the quality of the labels and the quality of the data. And you want to make sure that you are evaluating your models based on high quality data so that you're making proper decisions, like choosing the better of two prompts or choosing, whether or not to even deploy your machine learning model in the first place. I'm going to skip over that and jump to a natural, extension of detecting mislabeled data in a given data set would be, okay, if like you're going to have noisily labeled data because we have humans in the loop, a natural way to stem that, right, that most companies would use is having multiple data annotators who are responsible for labeling the data so that you have built-in redundancy. And you could have 3 annotators, label each data point and then try and extract, what's the best consensus label, how confident are we that consensus label is correct, and which annotators are not doing such a good job from such a data set. And the Cleanlab library actually contains a lot of algorithms to help you with this truth inference process in multi-annotator settings as well. And crucially, we want to work on settings where it's not, you have 3 annotators assigned to each data point, because that's a really wasteful way to have multiple people label data. So the Cleanlab library allows you to work on data sets where you have just maybe 1 annotator looking at some data points. Some data points might have 5 annotators who reviewed them. Really, you can have a heterogeneous matching between data points and annotators that allows you to use the fixed annotation budget much more efficiently. And again, the goals of the estimation would be to pull out, from these multiple annotations per image, a consensus label for each example that aggregates them into the best guess of what's the true label. Again, here we're just focusing on classification for simplicity, but the same ideas apply to other kinds of machine learning tasks. We'd want to estimate a quality score for the consensus label, that tells us how confident are we that this is actually correct. If we're really not confident, maybe you want to go ask another annotator or an expert to provide one more annotation, as well as being able to score each annotator and estimate the correctness of their labels. So I'm going to show just a tiny bit of math here, hopefully not too intimidating. But what we've designed here is another simple algorithm that we call CrowdLab to address all three of these estimation problems. And the key idea of CrowdLab, so there's, again, a huge, rich literature in the space of crowdsourcing with really complicated statistical probabilistic models and generative models that try and come up with ways to do this estimation. But again, in Cleanlab, our philosophy is use simple algorithms, but always combine them with machine learning models, and in particular, any machine learning model, such that this library can benefit, from any machine learning model, and the performance of the library will just keep improving as machine learning improves in the future. And so here, we're just going to assume you already have any kind of classifier model for your data, and you have its predictions, its probabilistic predictions, importantly, of what's the label given the features of each data point. And maybe you train this model, on some initial consensus labels, like from majority vote, say. And the reason, majority vote is not such a good method for addressing this estimation problem is, for example, you have some annotators who are much better than other annotators, right? And you don't want them to dominate your the bad annotators to dominate your majority vote. Another issue is you tend to have lots of ties, right? Because you'll have lots of examples where and the majority vote annotation would actually be a tie between maybe two classes. And thirdly, you would have a lot of data. If you're actually efficiently labeling a big data set, you really should have a lot of data where you're only having one annotator look at that data point. And majority vote, you're kind of just totally dependent then on the quality of that one annotator alone for getting a consensus label for that data point. So we are going to try and do better than that by leveraging this trained machine learning model we now have. And so, what's the best way to do this? So our solution that we offer in the Cleanlab open source library is to basically form an ensemble prediction of this machine learning model with predictions from each annotator. So we just pretend every single annotator themselves is a machine learning model. And then the most natural way to combine a bunch of machine learning predictions into one prediction is always weighted ensembling. So those of you who have participated in Kaggle or other machine learning competitions will see time and time again, that's the way to dominate these competitions, is to form a weighted ensemble predictor that combines the predictions with weights that essentially quantify how good is each predictor. So that's exactly what we do here. And we have an algorithm that you can refer to our published research paper to see the details of. But essentially, we have a way to estimate these weights. And the weights help us understand the trustworthiness of each annotator, both relative to the trained machine learning model as well as relative to each other. And the key idea to see in this formula here, why it's being shown, is that if we have, so this sum here is over all of the annotators who labeled data point I. And so if a ton of annotators happen to label data point I, then there's a lot of terms in the sum. And essentially, we're going to start disregarding the machine learning model, right? If I had 100 annotators labeled data point I actually don't really care what the machine learning model predicts, because I can pretty much see amongst these 100 annotators their disagreement will give me a good sense of how confident can I be in the consensus label. And even just the majority vote consensus label amongst 100 is like very reliable way to extract what's the best predictor of the truth. But on the flip side, if we only had a single annotator label this data point, then the sum is just over one annotator. And now we're starting to give a lot more weight to the machine learning model. And importantly, how much weight we're giving is based on how much we see how trustworthy the machine learning model tends to be overall versus this one annotator. So for the data points that were labeled by just one annotator, but the annotator was very untrustworthy, we might start to heavily rely on the machine learning model and be really suspicious when the machine learning model heavily disagrees with that one annotator.
And these are there's an iteration there too on those weights. Like as you learn more, you can continue to tweak how they balance against each other.
Exactly. So you can iterate this whole process. As I mentioned, this process was just taking in any machine learning model. I didn't really say, where this machine learning model is coming from. In practice, what we tend to do is train the original model on majority vote labels, or you can train it in a probabilistic way where you form, probabilistic labels based on all the annotators, like soft labels, it's called. But then once you have the machine learning model predictions, you now use them, right? to get your best guess of, the true consensus labels or probability distribution over the true consensus label. And then you can iterate this process and actually retrain the machine learning model with whatever are the current best consensus labels. And that process will actually converge
Mm,
after a few iterations. And that, yeah, we see consistently that actually gets you the best possible estimates of consensus labels.
nice. So we've got about 10 minutes left. I don't know where you are in your description here, but just bear that in mind.
Yeah, I'll probably jump over. I think now is a good time.
Okay.
So let's jump over and yeah, so here's our GitHub page, and you can find all our tutorials just from the GitHub page. And I'm going to just walk you really briefly through our canonical quick start tutorial. And so this platform within the package that is the platform for detecting all kinds of issues in a data set is, we call it Data-Lab, and it's specifically engineered to be super modular. So you as a user can even contribute your own, custom issue types, and Cleanlab will then run both the built-in issue type detections as well as your custom issue types together in a single test suite for your data set. And so the first ingredient, right, is to have machine learning model. In this tutorial here, we train a swim transformer machine learning model for image classification. This is the Caltech 256 data set, which is a pretty famous machine learning data set. And I'm not going to get too into the details here. It's just your standard, machine learning model training, nothing too exciting. And then we're going to extract those predicted class probabilities from trained machine learning models and its representations, its vector embeddings of each image in the data set. And we're going to save those. And that's pretty much the whole, that's the part that's on you as a user. You would provide this based on whatever machine learning model you have for your own project. And then you would start here with the Cleanlab code. So this is just fetching the data, showing this Caltech 256 data set, it's like a standard toy classification problem with different image categories like penguin. And I think this tutorial notebook here is just a subset of the data set for speed, like toad and penguin and other animal categories. And so we're gonna here just load these inputs. These are how our machine learning model views the data through its predicted class probabilities and its vector embeddings or feature representations of the data set. And then really the only code we need to run, as I showed before, is just this find issue method. And we're going to run Data-Lab here and say, that this is a labeled data set and here's the label. And it will run, and then it will say, here's the default types of issues I'm going to search for in this data set. And this set of issues that it's going to search for will depend by default on, what kinds of inputs are you providing. So if, for example, I only provided predictions and no embeddings of the data, then maybe some of the kinds of issue checks in the package that depend on features or embeddings will just automatically not be run. And so this package is very flexible. Like if you have more inputs that you've generated from your machine learning model, the package will use the more information you're providing and check for more kinds of data issues for you. But if you don't, that's fine too. And it'll just check for the issues it's able to based on whatever inputs you gave it.
Yeah.
And then based on that, it'll produce this report of, what seems to be wrong with your data set. And this report is, designed in a very minimal way to just convey the bare information you need to figure out what's wrong with your data set. Things like, so in this case, it's saying it detected many outliers, some near duplicates, some mislabeled data, and maybe that the data seems to be not independent. And the reason that the data seems to be not independent in this case is because it's actually sorted by class label. That's just the way the data was stored. And so the package help you detect, that that's something you should be aware of, because if your data is not independent, like future data may not look like your training data. And that's something there's no simple fix for. That's something that requires deep understanding of why your data, is not independent, and something to be severely concerned about. In this case, it's not a concern because it just happened to be that our training data was sorted by class. And so we can then, review the individual types of issues detected and see which data points themselves. So for each data point, we can see now, which data points are suffering from that issue type. and we get scores of how severe that issue type is for each data point. In the case of the duplicate issue type, the score would be quantifying how close semantically is this data point to the closest other data point in the data set. When this is 0, that means it's pretty much an exact duplicate and is an identical copy of another data point. And when it's non-zero, we're starting to say that it's not an exact duplicate, but it's semantically very similar. And so you can use different cutoffs on these scores if you don't like, our default thresholds that the library provides to you to determine which data points are actually exhibiting that issue or not. And then we can plot, some of these data points and, start to see, here's all the new duplicates in this data set that were detected. And so you can see, we're not only looking for exact duplicates, but, semantically similar pieces of information that you should, potentially be concerned about. And maybe a way to deal with all this would be maybe you delete all the near duplicates and just keep one of them. We can look at the mislabeled data again for each issue type. We can always dive into, what is the subset, how much is each data point exhibiting that issue, like how severe. And in mislabeled data, it would be like the probability that the package thinks this data point is mislabeled. And we can also get, what's the predicted label for this data point. That's just coming from your own machine learning model. And then we can look at, some of these mislabeled data points in this data set. Like here we have a data point labeled as a toad, but obviously not a toad. One labeled as an ibis, obviously not. So yeah, we can look at the outliers. Again, same exact thing, right? We're going to get for each data point, we're just filtering down to the data points detected to be an outlier here by filtering and then sorting them by their score. And we can plot them. And so here we're just plotting these outliers, and then we're plotting, the most similar images. This is just extra code we ran to help you compare most similar images in the data set with the given class label. And you can see, these are very abnormal images that don't even really belong to any of our classes here. And so, yeah, that gives you a basic idea, I think, of the value of this package. And I want to emphasize that we have this SaaS tool that complements this package called Cleanlab Studio. And in Cleanlab Studio, essentially, let me give you an image overview, maybe this one. In Cleanlab Studio, we are providing you the interfaces, to deal with all these problems. So like, not only will this detect, the mislabeled data, but then you can go and like quickly fix the data. And you can not only, fix data one at a time, but you can, fix like big subsets of the data all at once. Like here, we have a big subset of the data that was detected to all be mislabeled as shoes when there's actually this boot category in this retail data set. And so now we can filter down to all of these, and then we can, fix like a big chunk of them all at once, maybe say like the top 10. And so this is starting to help, a single data scientist can now clean up a big data set all at once. Hope I didn't apply the fix here. But yeah, this is starting to show you, how like a single data scientist can, fix a big data set all at once. And the other big difference in Cleanlab Studio is all of the machine learning is handled for you so that you don't necessarily even need to be a machine learning expert or have, this initial machine learning model. You just provide your data set and the tool will help you automatically find and fix all the problems in your data by using AutoML solutions that we have developed. I think
Excellent.
that's probably a good place to stop. And yeah, so I want to emphasize, use the open source library. If you have your own machine learning model, you have maybe some unique data set where this sort of AutoML solution in Cleanlab Studio won't really work for you. The open source library is super, super flexible and can really be applied to almost any data set that you're able to train a machine learning model for. It works for, all kinds of machine learning tasks, object detection, image segmentation, regression, entity recognition, and use Cleanlab Studio if you just want really quick results and you don't even know necessarily what's a great machine learning model, and you also want to actually fix your data set using a user interface that allows you to do it quickly.
Awesome. Thank you. So we're almost on time. We did have a question come in, was one I had as well. It's like, given where Cleanlab, the company and Cleanlab, the project have reached, what's up next? What are you working on? What are you trying? What features are you trying to add to the open source project and bring to the platform?
Yeah, so a big area that's ongoing for us is real-time issue detection. So far in the past, we've been really focused on this data prep phase of projects. And now we're, working with a lot of enterprise customers and big enterprises, and beyond, the data prep phase that the data scientists work on in most of their projects. They also want, embedded real-time issue detection.
Mhm.
You can imagine like a product catalog in an e-commerce company keeps having new products coming in, and each new product, the sellers are introducing all kinds of issues, and we want to detect those in real time. A deployed machine learning model during inference is given new data, which may have new kinds of issues, and we want to detect those in real time. That's a big focus of our open source library, and a big focus for our company. And the other big focus of all of this stuff is around foundation models and generative AI. Just the capabilities of these models is improving, immensely quickly. Like 2023 was a whirlwind year, expecting 2024 to be another one, where the capabilities of these models is improving so quickly. And most people are trying to use these models right in downstream applications, but we as a company are interested in using them to actually help you detect issues in your data and fix issues in your data. And we're just seeing the capabilities of these models is super strong in tasks like, data normalization, data cleaning, like all kinds of tasks where you can just get huge automated benefits. And long term, we think like building data cleaning agents is like a big direction for our company.
Excellent. Well, big adventures, lots to do, and lots of neat stuff to build. So I think we'll have to wrap it there. That's all for the event today. Jonas, thank you so much for your time. Thank you for being here and sharing all this about Cleanlab. Thank you to everyone who attended for the questions. As I said at the top, we are recording the event, and we'll get that up as soon as we can up onto our YouTube. Check out openteams.com to learn more about Open Teams and our offerings, and we'll see you at our next event. Thank you.